Another important property about stars is their temperature. Okay, so previously we talked about thermal radiation or blackbody radiation. This is the light that an object gives off simply because it is hot. Well, we learned that there were two laws that they follow. One is that as objects get harder, they become more luminous, that at all wavelengths they give off more light. And then second, we saw that the peak, what wavelength it was giving off the most light, got to shorter and shorter wavelengths, or they became bluer and bluer, as we got to higher and higher temperature. Okay, well, what this means is that red stars are relatively cool, and blue stars are relatively hot. And now notice I'm saying relatively. Cool stars, red stars, are still so hot they're giving off light. What this means is you still shouldn't touch them. Okay, blue stars are very, very hot. Absolutely don't touch them. Okay, well, we mentioned how we can actually use the entire spectrum to determine the temperature previously, but we can actually do something kind of clever so that we don't actually have to spend all the time to develop the entire spectrum. Instead, we can actually just use simple pictures. Our clever method is by using colored filters. So what colored filters do is they allow only a certain segment of color through the filter. Okay, so for example, a green filter lets green light through, a blue filter lets blue light through, and so on. Well, the most widely used filter set is the Johnson UBV set. It's actually UBVRI for red and infrared, but we're just looking at UB and V in this case. Okay, so U covers the ultraviolet, B covers blue, and V covers green. So U ultraviolet, B blue, V green. Okay, so this V actually stands for visual, because this is the part of the spectrum that our eyes are actually the most sensitive to. So it's true we see red and we see blue, but it's this green region that our eyes actually pick up the best. So what we can do is we can take a picture in two filters and then compare the brightness of the star in those two filters. Okay, so for example, looking at this middle star, this is actually our sun. We're going to take a picture in the ultraviolet and a picture in the blue. Okay, when we look at the ultraviolet and the blue, which of these filters is the sun going to appear brighter in? It's going to appear brighter in the blue filter. The sun gives off more blue light than it does ultraviolet, so it will be brighter in blue than in ultraviolet. So when we compare the blue and the ultraviolet, we see that it has more blue light than ultraviolet. We can do a little bit of math, specifically take the ratio, and that will then tell us the temperature of the sun. Only a star at 5800 Kelvin will have that exact ratio between ultraviolet and blue. Now then, do this for this other star. This other star is giving off lots and lots of ultraviolet, and also a lot of blue, but way more ultraviolet. So this star is going to be brighter in ultraviolet than it is in blue light. So when we form the ratio, we get a number, and only a star at 10,000 Kelvin is going to have that exact ratio. Okay, so in other words, we can simplify this process by simply taking pictures using colored filters. Well, so far, everything we've talked about is what we can do by just taking pictures. Just take a picture, you figure out the brightness. Take pictures at 2 different times of year, then you can get the parallax, which gives you the distance, and from brightness and distance, you figure out luminosity. Now, adding in the colored filters, we can now take 2 pictures, each in different colors, and then take the ratio, and that gives us the idea of temperature. However, we can get a lot more information if we start looking at the full spectrum of the stars. And so, we get this idea that taking the spectrum is going to be very useful. Well, as people first started taking spectra of stars, they noticed that there were variations and so on. Okay, well, anytime you start a new project, one of the first things you do is begin by classifying. So a group of astronomers started classifying stars on their spectrum, beginning with A. A-type stars were the ones that had the very darkest, hydrogen absorption lines. Okay, so remember back how absorption lines are formed. And if we have a very dark line, that means there has to be a lot of hydrogen present, or at least the hydrogen is absorbing a lot of light. Okay, so for example, over here, we have this hydrogen alpha line. Then over here, we've got the hydrogen beta. A-type stars are the ones that have these lines that are the very darkest. Okay, then ones that weren't as dark were labeled B, then ones that weren't as dark as that were labeled C, and the ones not as dark as that were D, and they went all the way through until O, so that an O-type star had no hydrogen absorption anywhere in its spectrum. Okay, the hydrogen absorption just wasn't there. So this was a nice categorization system. It worked, but it wasn't great. Some astronomers noticed that it worked well for the hydrogen absorption lines, but not for other lines. Okay, so notice we do have hydrogen here and over here, these hydrogen absorption lines, but we also get other things like magnesium and helium and these other things. And so it worked well for the hydrogen, but it didn't really work well for the other absorption lines. So a group at Harvard, which was headed by Edward Pickering, decided to recategorize. Okay, so this group of astronomers were known as the calculators, and they went through and they looked at all these spectra and decided to reorder them in a way that made more sense. Now, a picture of this group of astronomers, the calculators, is here in this image. Okay, and I'm going to point out, notice that they are all women. Now, this was done at the late 1800s, early 1900s. Not exactly a time of lots of women being allowed to do science. So this was actually really awesome. Now, that's something that is often pointed out in an astronomy class. Something that is not often pointed out is that they were allowed to stay in the basement categorizing all of these spectra. They were not allowed to actually take the data. Using the telescope was reserved for men. I know, it was a different time, things were weird, but that's the way it is. So, after recategorizing all of these things, this is the new order that they determined. They kept the same letters as before, but they rearranged them so that all of the spectra worked. Okay? All of the different absorption features would fade in and fade out. So, the new order is OBA-FG-KM. Now, this is something that helps us understand a lot about stars, so you are going to be required to know it. Okay, so OBA-FG-KM. A traditional mnemonic that I've seen in almost every astronomy textbook is "Oh, be a fine girl, kiss me," because astronomers are so advanced. Now, personally, I think that this is a silly phrase. It is stupid. So, I'm going to give you a challenge to come up with your own and better mnemonic. We're going to have a discussion board within this section. Put in your mnemonic for OBA-FG-KM. If you do, I will give you 5 points of extra credit. Then, I'm also going to allow the like feature in the discussion, and you can read through everybody else's suggestions and give them a like, and whichever one gets the most likes, I will give an additional 5 points of extra credit. Okay, so just doing it, you get 5 points. Doing the best one in the class gets you another 5 points. I'm actually really excited to see what you can come up with. Now, a quick warning. Because this is going to be publicly viewed, meaning that anybody in our class is going to be able to view it, please keep it PG-13. Okay, we've got some fun letters in here. We've got A and F. Okay, so please keep it PG-13. Now, one of the calculators, Annie Jump Canyon, she was actually kind of the head of the actual calculators, and she noticed that there was enough variation between each letter group that she could subdivide it. So the way she did this was by adding a number to the letter. So the spectral types range from O0 and then O1, O2, O3, and so on, all the way down to M9. Based on this categorizing system, the Sun is a G2 star. The Sun's spectral type is a G2. Now, when they first classified these things, they didn't know why this sequence worked. It did work, Things blended smoothly and nicely together, but exactly why, they didn't know. What we have since found out is that this is actually a temperature sequence. How well different atoms are able to absorb light is related to the temperature. So our O-type stars are so very hot that hydrogen can't absorb any light. The hydrogen atoms are too hot, they can't absorb the light. As we cool off over to an A-type star, these have the right temperature to have the maximum hydrogen absorption lines. As we continue to cool off, the hydrogen drops down, and other elements begin picking up, like iron and calcium. And in the very coolest stars, our M-type stars, these are actually so cool, we actually begin to see molecular absorption lines. We actually begin to see molecules within these. Now, don't think like molecules like water. Water would absolutely not survive these temperatures, but things like titanium oxide, which is really exciting. Now, from the spectrum, one of the things we can do is actually determine the composition. Well, what we have found is that stars are about 74% hydrogen, 25% helium, and less than 1% metals. Now, really quick, in astronomy, we have three things. There's hydrogen, helium, and the metals. Metals are everything else other than hydrogen and helium. And so you need to be careful what type of scientist you're talking to. If you're talking to a chemist, then you've got metals and nonmetals. Hydrogen and helium are nonmetals, okay, as is oxygen. But to an astronomer, the only nonmetals are hydrogen and helium. To an astronomer, oxygen is still considered a metal, because it's something that is not hydrogen or helium. So be aware, when I'm talking about metals in class, I mean everything else other than hydrogen and helium.